Hi everyone, welcome to the keynote session of IEEE PES Young Professional Powering the Future Summit. I cordially welcome you to this session actually, and I hope you are safe and sound wherever you are. Thank you for investing your time with us, and I hope the session will be fruitful for you. Um, so let's start. Accelerating innovation in power sector technology, especially in the light of quickly modernizing grid and requirements of a changing energy, makes it incredibly important for all of us. In the wake of major rolling blackouts and energy emergencies in 2020 and 2021, it's no secret that today's electric grid is being pushed to do more than what it is expected to do. Today, we have our distinguished speaker, Michael Pesin from US Department of Energy to talk more about this and speak on the topic Future of Energy. Michael Pesin is the Deputy Assistant Secretary of Advanced Grid Research and Development Division at the US Department of Energy's Office of Electricity. His organization is responsible for the development and management of the project for the next generation electricity delivering technologies and supporting activities to accelerate their introduction into the marketplace. Mr. Pesin has 30 years of experience in electric utility industry. Prior to joining DOE, Mr. Pesin was also the founder and president of the consulting company working with utilities, technology companies, and investors. He was a board member at several technology organizations and is actively involved with number of electric power industry groups and a speaker at different industry events. Sir, we cordially welcome you to the summit. IEEE Young Professionals Powering the Future Summit is honored to have you as our keynote speaker. We invite you to deliver the keynote address. The stage is yours, sir.
Good morning, good afternoon, good evening. Thank you very much for a nice introduction. It's my pleasure to be here. So I will talk about the challenges that we're facing today trying to decarbonize electric grid. So I will switch to my presentation and I will have to shut down my video feed just to preserve the bandwidth. So bear with me just for 1 second. Okay, I think you should be able to see this. So I will talk today about how do we get from where we are today with the electric grid to the future where we want to have decarbonized electric grid. As you know, United States President Biden established very aggressive goals for decarbonization. So we want to have fully decarbonized electric grid by 2035, and we want entire economy to be carbon neutral by 2050. It is a very aggressive goal and requires a lot of innovation. So Department of Energy has three main priorities established by Secretary Granholm. The first one is combating the climate change. So I don't need to tell you much about this. This is the biggest crisis our entire planet facing today. So what do we do in electric industry, electric power systems? How can we help to combat this crisis? Another objective is we want to create clean energy jobs. So we don't want anyone to be left behind in this new carbon-free economy. Whether those people are miners who might lose their jobs because these fossil power plants no longer going to exist and require coal or other fossil fuels, or it's people in some disadvantaged communities who carry the biggest burden of climate change, hurricanes, outages, blackouts. And the third objective is we want to promote the energy justice. So we want to make sure that everyone can benefit in this new economy. So it's not just goes to few wealthy people, that we equally distribute the values, the benefits of this clean energy. And we have clean air for everyone, we have resilient power for everyone, and we have access to new clean jobs for everyone. So why it is so important to address this climate change from the grid perspective? So this is the numbers just for United States, how much we spent in this country to recover electric power system from the major weather events. So in 90s, annual expenditures just to clean up after hurricanes for power grid was about from all hurricanes over the year was about $20 billion. In 1990, it grew to close to 30 billion. In 2000s, it skyrocketed to almost double, to almost $50 billion. In 2010s, it increased again to $80 billion. And just in past 5 years, we spent approximately $121 billion a year to recover from major weather events. There is no denial that it's going to be only getting worse if we don't do something about climate. So it's not a question of do we need to do it? The question is how fast can we do it? So the other objective of the department is to support United States manufacturing. So we are committed to research, development, demonstration efforts that would lead to domestic manufacturing of advanced energy systems. And again, it will enable creation of new jobs for everyone. And energy justice. So one of the new initiatives that we launched is called Local Energy Action Program, or Communities Leap. So this initiative is designed to help environmental justice communities and communities with historical ties to fossil fuel industries to take direct control of their future. So we'll be investing a lot of money to help in this community. So we'll have up to $16 million for each community to help them to develop new approaches to their energy future. And the biggest value is that they will have access to department's national laboratories. So DOE has 17 national laboratories that have some unparalleled expertise. It's a crown jewel of our departments, our economy, our science. And those laboratories will be available to help develop new plans for those communities. So let's talk about power grid. And you might know about this already a lot, so I'm not going to spend much time on this, but I just want to give you overview of what we're seeing today and what is changing, and then I'll go and talk about challenges that those changes are presenting to us. So electric grid was designed over 130 years ago. And the way it was built, the main purpose of electric grid was to keep the lights on. It was organized in a way that you had centralized generation that was mostly fossil, some hydro, and this electricity was then transmitted over transmission lines. Then it would go to substation, and the substation would lower the voltage. It would go to distribution lines, and then from distribution lines would bring this electricity to customers. So there's 3 different types of customers. Most utilities have customer categories: commercial, residential, industrial, and this is how it was operated for over 100 years. So today we see a number of changes that has been happening. So the first one I will talk about is much higher penetration of renewable generation. So the generation portfolio mix is changing drastically. So we have more solar and wind coming online. Solar and wind has very different characteristics. I'll talk about this. We also have much more reliance on natural gas. The interesting thing about natural gas is it has its own infrastructure, its own delivery infrastructure. So now those 2 infrastructures, electricity and natural gas, become very tightly coupled, interdependent. So the threat to one infrastructure poses same threat to another infrastructure. So we need to address that. The other challenge, if you look at the other side, we now have a lot of distributed energy resources. Those distributed energy resources now create electricity on the other side of the electric grid, where it was not created, never was created before. So we need to address this. Then we have completely new types of loads coming on the grid, with new demands for these loads, with new expectations for service. So electrification of transportation. There is a big push to electrify vehicles, electrify all transportation. So there's 2 different options. One is battery-powered vehicles, another one hydrogen, but I'll focus today more on battery-powered vehicles. So those vehicles present challenges and opportunities. And I'll talk a little bit more about this as well. And last but not least, consumers now have expectations that they can participate in electricity markets. So in United States, we have, so Department of Energy is not a regulatory agency. We have another agency called FERC, Federal Energy Regulatory Commission. And they just issued an order called Order 2222. And what it does, it allows all loads or all resources at the distribution side to participate in wholesale markets. It will have tremendous implications. That means that any organization, any consumer, they can aggregate their resources, whether it's generation, electric vehicles, storage, and they can provide services to the entire electric grid, whether it's frequency support or it's any type of service you can think of. If they have ability to do this, they can provide. So those are a lot of changes. And you see there's in the middle, so this is what Office of Electricity, the office that I'm representing, is responsible for. So we are responsible for this middle portion. We are responsible for transmission and distribution, which is industry calls T&D. And I starting to go away from this terminology, and I'll explain why. I'm starting to call it EDS, Electricity Delivery System. So you should not look at transmission, distribution, and installation anymore. So I'll talk about this in a second. And there is another block there, square there, grid storage or energy storage, and you see it in all three components of the electric grid. So it's not by accident it's there. It's becoming so important. We have to focus on this. We have to make big effort in developing this. And again, I'll talk about this as well. So this is the kind of preview of what I want to talk about. So those are the changes and those are the challenges. While we implemented those changes, we also had another revolution, internet, right? So now we have communication that covers the entire globe, and it used for electric grid as well. So we have what we call ICT, Information and Communication Technology, that is embedded almost in every segment of the electric grid. It has other implications than just on electric power. It has implications on cybersecurity. So cybersecurity is one of the very big areas of effort at the Department of Energy. So what we're doing today, we're changing how we approach cybersecurity. In the past, when you deploy a project, a system, you would look at this and think, well, how do we need to protect it? What needs to be done to protect it from malicious cyber attacks or from failures of the communication networks that can have negative consequences? Today, we're doing what we call security by design or engineered security. And security by design means that when we start any R&D process, one of the steps in this process is to analyze what are the potential cybersecurity implications for this development. Not all developments will require cybersecurity component. So, for example, when you're developing new conductors, there is nothing that can be done to conductors from cyberspace. But today, you'll be surprised how many other components that you wouldn't think have cyber implications now have it. From circuit breakers to transformers to any sensors that you deploy in the network, any communication component, cybersecurity becoming increasingly important. So that's enough on the high level. So let me dive a little bit deeper on this. So I talked about changing in generation portfolio. So one of the characteristics of especially solar and wind, that is highest percentage of renewables coming online, is that they're not fully dispatchable, they're intermittent or variable. So the way we operated electric grid for last 100+ years, we were able to pretty accurately forecast your loads, and then we were able to control your generation to make sure that you match your demand. So today, you need to forecast both your generation and loads, which makes it very difficult and makes it very different how you operate electric grid. So all of you had math at high school. So if you have equation that now has two variables, you can't really solve it, right? So you need to have second equation. So you need to have system of equations to solve it. So same way in electric grid, you need to have another components, another parameter that helps you to solve those equations. And that parameter is flexibility. So you need to have flexible grid. And there is several ways to achieve this flexibility. So this picture is this from this study that we've done at NREL, National Renewable Energy Labs, and it shows you what are the tools that we have at our disposal to improve flexibility to accommodate high penetration of variable renewable generation. So one, we can improve system operations and forecasting. Another one, we can increase use of grid services from variable renewable energy, meaning you'd have to be able to control to some degree these renewable energy resources. Then we can enable a load and demand response. So you can control another side of the equation. So you can control your loads, and if you do it in real time, it can be done. There's a lot of very interesting work that is happening on this one, because if you want to have it part of your ecosystem that is electric power system, you need to be able to have some assurances that the services can be reliable and secure. So we look at the different tools, like we applying blockchain to make sure that we have secure controls and record of all the transactions, right? Because we're talking about market, right? So it's not just technology, it's the markets and policies that need to affect it. I'll talk about this later. But we want to make sure that we have immutable records of all the transactions that are happening on the grid, because now you have very complex relationships. So today you have what we call one-to-many relationship, right? You have one system operator, and the system operator has a relationship with many components, which are generators and some loads, substations. But you're going to have many-to-many relationship, which means many consumers will be interacting with many other connection points. So you're talking about IoT, Internet of Things, or what we call industrial Internet of Things. So it requires a lot of work, and we're working on this. And then flexible operations. So we need to have operations that are not static, that are not designed by template, but that are flexible based on your conditions, based on changing environment, based on changing threats. And transmission, I'll talk about this separately, but transmission, we need a lot more transmission to be built. And we need to have different ways how we operate this transmission. So, and last but not least, and this, if you notice, is bolded here because I will come back to that, we need a lot of storage. We need all kinds of storage. We need storage that can support your frequency, which is very fast storage that can store it for seconds or minutes, to all the way to days, weeks, months, seasons. So we need seasonal storage in order to be able to support decarbonized grid. The other interesting characteristic of most renewable generation resources, which is, as I mentioned, mostly solar and wind, is that unlike traditional fossil and nuclear and hydro, they are inverter-based. So what does it mean? So the traditional generation, the way it is producing electricity, it has very large generators or rotating machinery. Those generators have big stator and rotor, and it's very heavy. It's very big rotating mass. So because this is a heavy rotating mass, it has a lot of inertia. So when something happens, when an event happens on the system, this inertia doesn't allow this event to propagate, to become much worse quickly, right? It kind of slows it down. It pulls it back. It holds this frequency. So it helps to maintain grid stability, grid operations. And we always, for the last 100 years, we relied on this inertia to make sure that our grid is stable, that we maintain our frequency. Well, in the United States, it's 60 hertz. In most other countries, it's 50 hertz. But we have to be as close to this 50 or 60 hertz as possible. And inertia is one of the tools that helps us with this. Now, the new type of generation does not have this rotating machinery. They have inverters that interface between this generation source and electric grid. So solar, wind, natively DC, direct current. So in order for them to be connected to AC grid, we need to convert it to AC. This is what inverters do. But when you have the disturbance on the system, now you don't have this rotating machinery, rotating mass to slow it down. So you can have a catastrophic impact from even minor disturbance if you have a lot of these inverter-based resources on the system. So we need to address that. So what are the main challenges? How do we address that? So one thing is frequency support. As I mentioned, you want to stay as close to your fundamental frequency, 50 or 60, as possible. So you need to be able to do it by other means. So one of the ways to do it is what we call synthetic inertia. So you can have this here in this picture, smart PV and smart wind. So we can send the control signal to mimic the inertia. How would rotating machinery react to this signal? So synthetic inertia is one of them. But we also need to be able to support voltage and reactive power. We also need to be able to form electric grid forming capability, basically the ability to generate the right frequency, right? So not just to follow the frequency of the grid, but to be able to dictate what the frequency should be. And then black start. So when the system falls apart in unlikely events, but it's possible, right? If you need to bring it back up. Today you can do it with rotating machinery because it will set your frequency, and you can put together your grid like your Lego blocks together. If you don't have this, you need to find other ways to do it. So we developed the program on how to do it with high penetration of renewables. So we can do it now with solar and wind. Again, fortunately, we never had to do this, but it is possible. The other challenge is protection. So protection is a fundamental function of electric grid. So protection is very important. Protection is when you have a fault on the line or anywhere in the system, you need to be able to isolate this fault. Otherwise, you will cause catastrophic damage to a lot of equipment. And it also presents a lot of danger to human life. So you need to protect your equipment and you need to protect human lives. So this is what protection is doing. And most of the time, most of the protection system, the primary way they protect or identify the problem is by overcurrent conditions. So when you have the fault, so your impedance, your resistance impedance is significantly reduced, and your fault current goes high, so you can see this high current, and you can open the circuit breaker and isolate the fault. So with inverter-based resources, your fault current is significantly lower. So you might not always able to see overcurrent conditions when you have fault. So it becomes tricky. So what we're doing is we're developing different mechanisms, different ways to protect the system based on signatures. So we have high fidelity sensors that can recognize signature of the fault, and it can detect the fault based on the signature and then isolate this fault to prevent damage and threat to human life. What's interesting about this approach is it's not only we can detect faults, but we can also detect any other anomalies on the grid. So oftentimes we can see precursors of the fault. So we can identify something that will be happening in the future and prevent this event from happening. So we can see equipment starting to fail. We can see conductors being broken but not causing fault yet. So there is a lot of things we can detect by using high fidelity sensing, and this is what another thing they're working on in my area. And then control system interactions and resonances. Now, when you have a lot of these control systems, they start interacting in unexpected ways. So you want to avoid creating a resonance frequency, or you want to avoid creating any undesirable effects from interaction between this control system. So we've done a lot of studies on that. We've done some pilot projects. So that is the other challenge that we're facing. The other issue that is coming up, and I mentioned this with generation now being on both sides of electric grid. Now we have bidirectional flows that grid is not designed today to handle. So we need to have very agile system to manage this, to handle this. So the impact of the distributed energy resources it has on many components. One is, I mentioned, system protection. So not only we have difficulty detecting faults due to the low fault current, but now we have power flow in the direction where it did not expect to go, so it can be misinterpreted as fault. So we need to go through system and analyze how to design it. The other challenge is, and we already have seen it happening more than once, is when you have a lot of solar resources and you have a fault, how do you ride through this fault? So if you have inverters that see voltage drop during the fault, they can take themselves offline, which will make situation even worse. So system will collapse because now you not only have fault, but now you lost a lot of your generation. So you can't serve all loads. So we want to be able to ride through faults. So the IEEE standard 1547 is addressing those issues. And then I mentioned FERC Order 2222 that allows you to aggregate your resources on distribution side to support your bulk operations. So how do we do this? So again, we developing new mechanisms, new tools, new policies. How do we compensate consumers for that? Using secure mechanisms such as blockchain. So this is all that we need to do. And then we need to manage transmission flows without today we don't see what's happening on the distribution side. So we have system operators. So in the United States, we have ISOs, which are independent system operators, and then we have TSO, we have independent system operators and TSOs, transmission system operators. So they don't have ability to see today beyond their transmission systems. So we need to give them this visibility, give them this capability to have situational awareness. So what does it mean for the grid? What does it mean for the transmission system? So in case you didn't see it yet, I will summarize it for you. So we're not just changing, we're not just facing gradual change. We're facing step change. It's a drastic change. It's not evolution, it is a revolution. And this revolution is happening in the way we produce electricity, in the way we deliver electricity, and the way consumers or loads interact with electricity. And it will affect pretty much every aspect of our work. It will affect how you design the grid, how you operate the grid, and how you protect the grid. So, because future grid will need to be handled bidirectional flow of electricity. We need to figure out how to apply alternative grid configuration. I'll talk about in a second. How to coordinate planning and operations across multiple participants, because right now you have your transmission, you have a distribution. So I mentioned earlier that I stopped calling it T&D and start calling this delivery system EDS. And the reason why is because now transmission and distribution system are so closely coupled together. So the line between them is really blurring. Yes, equipment is different because of different classes of voltages, but the way you operate, you cannot operate transmission system without considering your distribution system anymore. So you need to look at this as one system: transmission, distribution, electricity delivery system. And implications going to be in every single part of the delivery system. So we have interregional transmission. And for that transmission, we need more effective utilization of generation resources. The way to make it possible is, in the United States, we have actually 3 electric grids, right? So it's not one grid, it's 3 grids. It's East, West, and Texas. And those grids are connected through SIMs, through back-to-back DC links that are isolated for the operations. So it helps you somewhat with reliability, but at the same time, it does not allow you to fully utilize all the resources across the entire country. So, for example, we can't take advantage of excess wind generation in Midwest to support charging for electric vehicles at night in California when there is no solar power available to charge them. So we want to be able to take advantage of that. But for that, we need to strengthen those interconnects between those grids. It doesn't mean we need to connect them into one grid, but we need to make sure that those interconnects are much stronger. Then regional transmission. So regional transmission now is starting to have different role. It's becoming like a collector for all your renewable generation resources. So the renewable generation is typically not co-located with your load centers, which means you need to get this electricity and bring it to load centers. For that, you need to have a lot of transmission. So you need to build new transmission, you need to modernize existing transmission. Again, I'll talk more about this in a second. And then, of course, distribution system, because right now, not only you have bidirectional flows on the distribution system, but you have a lot more types of connected resources to the system. Electric vehicles, which is a whole other topic. What is the impact on distribution system? So there was a lot of analysis been done. So it's not as bad as originally people thought. So there may be some impact on distribution transformers being overloaded, but those are easy to replace. It's easier than addressing the global impact of those electric vehicles with need of more generation, ability to bring this electricity to where it needs to go. So we're working on how to make sure those electric vehicles can be served by existing system. And the way we look at this, this is approach from two directions. So from one side, we want to make sure that electric grid has the ability to support all these new loads, all these new electric vehicles. But on the other hand, we want to make sure that those electric vehicles can provide support to the grid. So we're looking into the different mechanisms, smart charging. So how do you enable the way that electric vehicles charge so they don't have a lot of negative impact on the grid? The other big opportunity is V2G, or vehicle to grid. This is an ability of electric vehicle batteries to put power back into the grid when it needs it. And again, but this is not just technical issue, this is a policy and market issue. Because why would owner of electric vehicle want to do this, right? Yeah, maybe some of them might want to do it for altruistic purposes, but most people in market economy, they expect to be compensated for services they provide. So we are developing markets and mechanisms how to compensate people for providing these services to the grid. Again, we're using different types of technologies. I mentioned blockchain is one of those. We're using different aggregation services because it's much easier to control a large group of loads versus controlling individual ones. So a lot of work is done in this space. And then transmission, I promised I'll come back to that. So we need a lot more transmission in order to enable decarbonized grid. So transmission is critical to connect renewables to the grid. Within region, you need to have more transmission. You need to have more transmission across regions and across these three interconnects that I mentioned. So we had a lot of studies done on that, and most of the studies come to the conclusion that we need about 50% more transmission capacity than we have today to have truly decarbonized electric grid in the United States. And if we have this interregional transmission, we can have significant financial benefit by doing this. So the estimate is about 180 billion, and this is not including benefits of reliability and resilience. This is just for accommodating renewable generation. So, but there are two ways to increase transmission capacity. So one way is to build new transmission lines. Unfortunately, at least in the United States, it takes very long time to build new transmission. It can take years, it can take a decade before you can build transmission lines while you go through all the processes. So the other way to do it is to increase capacity of existing transmission. Most transmission lines capacity is underutilized. The way transmission lines are operated is based on the tables that tell you what is the ampacity or amount of power you can transmit based on the temperature, ambient temperature. But you can do much better. We can enable what we call dynamic line rating. So we can deploy sensors that will show you what is the real conditions, and it can allow you to increase capacity of transmission line in real time. And we had some studies that shows you can do it, you can increase your capacity about up to 30%, 30, up to 30% just by doing this. So, but then we don't stop there. We're looking into different ways with new components. Again, if you have time, I'll talk about this as well. And then how to operate the grid. So we need to operate it very differently. So as I mentioned, we have a lot more control nodes. Right now, today, if you see on the right-hand side, the present grid is you have just centralized generation and you have some limited number of energy sources or distributed energy resources on the other side. On the right of this picture, you see future grid where you have much fewer synchronous generators. You have more variable inverter-based operations, more distributed generation and controllable loads. So you need to operate it completely differently. So, and then you need to change how you plan. So now you have multiple routes to decarbonize electric grids. So you need to accommodate variable nature of renewable energy. You need to consider electrification of your all energy sectors. So it's not just transportation. There is a push for bigger electrification for entire industry. So we need to include it in our planning. And interdependence. So I mentioned earlier that now you have new interdependence between electricity and natural gas. But this is not just electricity and natural gas. There is interdependence between electricity, transportation, water, communications, transmission, distribution, storage. So a lot of the industries, a lot of the systems are not only dependent on the electric grid, but also electric grid is dependent on those systems. So we need to consider this. So one of the things, very briefly, I just mentioned is we created last 3 years, we developed a model that we call NARM, North American Energy Resiliency Model, that allows you to model all interdependent infrastructures across the entire North American electric grid, which includes United States, Canada, and a small part of Mexico. So we have this tool today, but we need to start using this tool more and more, because we have more and more reliance on other infrastructures that we can't ignore. And that requires us to develop a lot of new analytical tools. We need to have new business models. We need to create new markets. We need to make sure we have policies that support those markets. So all of the things that we work in. So I'm going very fast, so I have some time left for the questions, but I think you're going to have the slides so you can look at this. So DOE, as I mentioned, is not a regulatory agency. But what we're doing, we're providing technical assistance to other agencies, which is like Federal Energy Regulatory Commission, NERC, the way United States, the FERC regulates your transmission system, your bulk system, but local distribution utilities are regulated by states. So we're working with states to provide them technical assistance and advice on what is the best way to go into decarbonized future. What policies need to be enacted, what projects need to be approved. So we're providing this technical expertise. So those are the challenges. What do we need to address them? So if I were to simplify this, if I want to put it as simple as possible, we need to start with two things. We need to have improved visibility and situational awareness. So we need to be able to see, right? So very simple. If you don't see it, you can't control it. To enable good visibility, you need to have sensing. You need to have a lot of sensors that allows you to collect all this information. Then you need to get this data from sensors somewhere where it can be analyzed, or sometimes it can be some analysis can be done locally. You can have distributed computing, and then you can have computing capabilities, data analytics, and because there is such a huge amount of data now, it's a big data coming. We are employing more and more artificial intelligence, machine learning, to be able to process this data and make sense out of this data. And then we need to be able to control what we see, right? So we need to have better controllability. So I talked about dynamic line rating, but this is just the first step. So once you see it and you can change your operations based on your available information, now you can start applying different control mechanisms. So today, grid is very static, right? It's similar to your highway system. So you have several exits, and you can close some exits, you can close some lanes, you can add additional lane to highway, but it doesn't change the nature of how your grid operates. What we will see likely in the future is what I call electricity network. So we will transition from electric grid to electric network that is more similar to internet today. So in internet, you have multiple ways to get your data packet from point A to point Z. So you can go through A, B, C, D, and you can choose your entire alphabet soup where it goes. The way it works on the internet world, you have these routers, and routers, they have a lot of information about all the paths they can get packet from one point to another. And what those routers do, they calculate what it's called optimal path. So they assign cost of path to each segment of the internet. And they calculate what is the least cost path to get from point A to point Z. And then they route your data packet the same way. We want to see the same thing happening with electricity. So when you have this complex electric grid that is interconnected, you have full visibility and situational awareness. You have full ability to control it. Then you can optimize how your power flows from point A to point Z. So you can choose the route. Of course, the flow of electricity is governed not by laws that we can enact in FERC or Congress. It's governed by laws of physics, which we can't change. But what we can do, we can change physical parameters of the system. So there are some devices we're developing, some of them called power flow controllers. So we can install those devices on transmission lines to change impedances of those lines to force power to flow where you want it to go. One other technology that will be tremendous help to the future grid is HVDC. So today, most of the grid is alternating current. And probably most of you heard the story of current wars back in 19th century. And the reason AC won because there was no technology at the time to convert direct current into higher voltage and transmit it for long distances. And that's the main reason behind AC grid today. Now, today, we can have this technology. I mean, technologies exist today, but right now it's very expensive. So that's why you only see HVDC lines when they go over long distances for long distance, because this is when you have this economies of scale, because the termination equipment, the terminal points are very expensive. But if we invest in new technologies and we make it more efficient and less expensive, we can have more DC introduced to the electric grid. I'm not saying that we will transition to DC grid. What I'm saying is we're going to have more DC segments in the grid, and in critical locations where it makes sense. But that will help a lot with many things, with integration of renewables, with resilience, with reliability. DC is much better. We have better losses. And other thing it will help a lot is with increased capacity, right? I was talking about how important, how urgent is need to increase capacity of transmission system. So if you convert a C line to DC line, immediately you can triple the capacity in the same right away. And if you, at the same time, if you raise voltage, you can increase the capacity even more. So converting AC lines to DC lines will give you a lot of value, a lot of benefits. But we need to work on better HVDC technologies. So this is probably the most interesting slide, at least for me, in this presentation. So let me talk about this, and then if you have questions, you can ask me later. So I just described to you changes, challenges, but what is the future? What the future will look like? So if I had a crystal ball and I will look in this crystal ball, which by the way I don't have, I think those are the things that I would see floating there. So there's two scenarios that have been discussed by the industry. So if you look at this picture, on the lower left corner is what we have today. We have transmission distribution system. It's very rigid. So in other words, if you have problem on one part of the system, it propagates through entire system many times. It's very capital intensive, which means you have a lot of expensive equipment. If you want to build nuclear power plant, it takes a lot of money. Transmission lines are very expensive. So, but this is how it works today. So one scenario, if you go up on the left-hand side, it is a scenario when what I was describing a lot today is when you increase your transmission capacity, you build a lot of new transmission, you increase existing transmission capacity, you put a lot of AC/DC grid, and you need to put a lot of storage because you need storage to integrate your intermittent variable resources. And then you'll end up with this very strong, very expensive, but very large grid that is pretty flexible, because now you have a lot of storage, but it's still very capital intensive. Now, if you go to the other scenario, if you go in horizontal axis and you go to the lower right corner, you'll see the other scenario where you have completely distributed electric system. In this scenario, some might say you no longer need grid at all. You have all your generation you need locally. You can have you can supply your electricity from the local sources. You don't need to rely on anything from the larger grid. We have our nuclear energy office is working on micro nuclear reactors. So eventually, at some point of time, you might have those micro nuclear reactors in every neighborhood. Or one day we may invent cold fusion, and then you can have your generation size of your refrigerator in your basement. Who knows? But I don't see it happening in our lifetimes. So, but this is another scenario. But what my crystal ball shows me is the combination. It's a hybrid world where you need, yes, you will have a lot of distributed energy resources. You will have ability to support some of your local resources with local generation. But you still need to rely on this large grid because, first of all, economies at scale never going to go away. It's again until you invent something drastic like cold fusion. But I'm kind of half kidding, but it might happen one day. But I don't see it happening in the near future. So you still need to rely on this big grid. It's not going to go away. We still need it. But at the same time, we should not ignore opportunities on the distribution side, on the distributed resources. So what we need is what this diagonal arrow is showing on this picture. We need to have variable, integrative, and flexible grid across both transmission, distribution, and customers. So that's why I'm calling EDS. Electricity delivery system needs to be fully integrated. And at some point, I don't call it EDSC. I don't add customers there just yet. But one day you might. You might have to. Customers may become part of your portfolio because they're going to be, if they're going to be fully controllable, whether it's from distributed computing capabilities or they will be controlled by centralized signal using some secure mechanisms with blockchain, with whatever mechanisms are. So we need this. But what we know is that next generation electricity network will need to be able to control all flexible generation and all flexible loads on customer side. We need to have a lot of energy storage. There is no doubt about this. We need to be able to figure out how to make sure we have enough synthetic inertia there. And we need to have multi-directional power flow. So we need to have ability to support this generation. So this is all that needs to happen. And this is what we're working on. So I'll just very briefly, because we're almost out of time, I will very briefly talk about what we're doing. So there's 5 main areas on the transmission side. We're looking at new grid operations, new distribution integrated with transmission operations. We need to have automatic control systems because humans can't be fast enough to control the systems. We need to have hardware components. I mentioned this already. And we need to have economic tools and planning tools. And on microgrids, again, microgrids can provide a lot of value. So we're no longer looking at microgrids as they looked at them in the past, which is for 2 purposes, mostly improved resilience and integration of renewables. We're looking at microgrids as something that is capable of becoming a building block of electric grid. So it is a building block. So you have this design of the grid that coming all the way down from individual solar panel, individual load, all the way up to the bulk system. And this is becoming one ecosystem. So I think this is all the time I had today because I want to leave some time for questions. And I think I will jump to questions at this point. So thank you very much.
Hi, sir. So thank you for a very informative session. So we have one question from Professor Felipe Lopez. So I will read it out to you. Different control strategies it completely changes the system response during faults. How to deal with these uncertainties? Should we look towards the specific features of each system?
Yes, this is very, very good question. So it does change what happens during the fault. And it depends, I guess, there are different types of faults, right? So if you look at distribution system, I think this is not what you're asking. I'm guessing your question more about the bulk system, transmission system, how system responds to that. So the first thing is you want to isolate the fault. So this is you always first action you need to do. And in order to be able to isolate the fault, you want to be able to detect the fault. This is what I was talking about when I talked about new protection mechanisms. So instead of identifying overcurrent conditions, you have to identify signature of the fault. But then what's more complex is the system stability, like dynamics. So I don't have a short answer to that. I'll try to summarize it in big terms. So you need to be able to employ multiple resources to mitigate your faults. Because the faults, if you have high penetration of renewables, when you have a fault, when you don't have the system inertia, you can go out of frequency very far too quickly, and then your system will fall apart. So one way to do it, one way to address it is to have much better visibility in what's happening in the real world, and then engage your resources to respond to the effect that this fault caused. So I can't go really deep in this because without going to the much technical studies that you've done, but this is my kind of very, very high level answer.
Thank you for answering our question, sir. And thank you for the question, Professor Felipe Lopez. And we have one question from Rahul. How to economically convert HVAC transmission to HVDC transmission?
Yes. So HVDC, there's a lot of work being done in this space. So the challenge with HVDC is its economy at scale, right? So there is private industry needs incentives to invest in R&D and new technologies. There is not too much market for extra high voltage DC transmission. So there's few things that we are now trying to do. So first of all, new technology, new R&D. So we trying to employ new types of semiconductors. So silicon carbide, for example, is something the silicon carbide we are using for high voltage DC transmission. We're also looking at gallium nitride, which is again, but wide gap semiconductors have big promise for HVDC transmission. So wide gap semiconductor research is ongoing. But the other way to answer this question is DC is everywhere. So it's not just in high voltage DC. So what we're trying to do, we're trying to leverage investment in research in DC so we can utilize it for both HVDC and other solid state devices. So by the way, HVDC is not the only application we need for the grid. So medium voltage DC, even though HVDC is kind of what I talked a lot about, but for example, for offshore wind, the best solution would be medium voltage direct current, because this is the best way to create a mesh and connect this from offshore and bring it back to the shore. But they also have a lot of DC, which is native to many other things, such as wind and solar. So if we invest in R&D research for solid state components, we can leverage this investment for all of them, because at some point, if you have, for example, charging stations for electric vehicles, fast charging, and it can operate at 1000 volts level, it might quite possibly have same components that you can just stack up to bring it to the higher voltage. You can stack those 1000 of those, for example. I'm not saying we can do it, but it's just one of the possibilities. And you can create the 1000 kilovolt system. So if you develop individual components, which has much better market opportunities, you will see a lot more investment from private industry in this. And of course, federal government in the United States, we support early stage R&D, and we invest in technologies that private industry would not necessarily invest because the risk is too high or market is not large enough. So what we're doing is we're working with private industry to help us investments. But it is very important. I think it's next to in importance to energy storage. So energy storage, I would put number one right now in terms of importance of developing, reducing costs, improving performance, and HVDC and in general power electronics would be next to that.
Thank you for the answer, sir, and thank you for the question, Rahul. I think we have come to the end of this session, and first of all, I would like to thank our distinguished speaker, Michael Pesin, for delivering such an informative talk. And we are really honored to have you, and it was a very wonderful session. And thank you, sir, for spending your time with us and sharing your knowledge with us.
Thank you. My pleasure. My pleasure. Thank you very much.
Thank you, sir. So I think it's time that we can end our session. So we have another session by Professor Zhu in 15 minutes. So I request all the participants to join our live session, and also after that we will be having a small quiz and a networking session in the breakout room. I request all of you to join that as well so that we can learn together. So the questions will be based on these presentations given by our distinguished speakers. So once again, thank you, sir.
Thank you.